In this video we are going to see some results which are going to be useful while proving primary decomposition theorem. Okay. Let us start with the definition of projection. Definition. So let V be a finite dimensional vector space over a field F, and let V be written as direct sum of subspace S1 and S2. Okay. Direct sum of S1 and S2. Okay. Now we say and we say let F be and let F be a linear map from V to V. F be a linear map from V to V. Okay. F is said to be a projection. F is said to be a projection map, to be a projection along S1 and onto S2. But this tells you the direction of the projection and also the the onto image of the projection, image of F. Okay, along and onto S2, along S1 and onto S2. Along S2, if f of V, okay, so since V is written as S1 plus S2, then we know that so we can easily say that since V is equal to S1 plus S2, then we know that by the definition of direct sum, we know that for all V in V, there exists unique S1 in S1 and S2 in S2 such that V can be written as S1 plus S2. Okay. So, we will use this here. F of V, which is nothing but F of S1 plus S2, okay, by this, and we say that this is equal to S2, okay, because on to S2. Then we say that's the definition of a projection. Okay. So, a linear map V from V to V is said to be a projection if is said to be a projection along S1 and onto S2 if f of V is equal to S2. Okay. So, you can easily notice that from here it is easy to notice that kernel of f is S1 and image of f is S2. Okay. So, that is easy to estimate, and therefore, therefore the projection is is a map along the direction of the kernel of f and onto S2. Okay. So, this can be easily understood. Similarly, if you want to change the direction of this, one trivial thing that we do normally we know is if you can say I minus f will also be a linear map from V to V, because L of V comma V you can add and subtract the linear maps. I minus f is also linear map from V to V, and if you notice it here, I minus f is going to be the kernel of I minus f. The kernel of I minus f will be image of f, and image of I minus f is the kernel of f. This is easy to estimate. It comes directly from this, and therefore you can say that I minus f will be a projection onto kernel of f along the direction of image of f, and therefore if you want to change the direction of projections, you can always do that. Okay. So, this is a thing. So, this is the definition of projections, and we know, we have trivial projections, identity map and zero maps are trivial projections, and we also have a lot of non-trivial projections. You can see that. Another thing that you need to observe here is by definition itself, it says that it fixes the every element of S2. That means what it says is for all x in S2, f of x is x. Okay, it fixes the every element of S2. That's very important thing that we have to observe that. Okay. Therefore, this will help you to look at given to check whether given linear map is a projection or not. This observation will be very helpful. Okay. In fact, we can also think of the the converse of this definition. In other words, what I mean to say is, suppose we have a given linear map f from V to V. Okay. And let us assume that V is direct sum of image of f plus kernel of f. Okay. And if f restricted to image of f is an identity map, then f is a projection. Then f is a projection along kernel of f and onto image of f. Okay. So, this should be clear. That's what we want to do. So therefore the definition should be the definition of projection is clear. Okay. Now let's look at some way to characterize this projection. Okay. So if you observe this definition, it says f of v is nothing but f of s1 plus s2, because v is direct sum of s1 plus s2, which is equal to s2. Okay. Now what is f of v now? F of v is f of s2. Okay. And we know it fixes every element of image of f, therefore it fixes every element of s2 because the projection map, and therefore f of s2 is also s2 again, right? Yes, f of s2 is s2, and that is nothing but what? F of s1 plus s2, that is f of v, right? Therefore what you get is f of v is f of v for all v in v. That this implies f square is f. Okay, that means and we know this is such a linear maps are called idempotent operators, idempotent linear map. Okay, therefore this kind of gives you a necessary condition for this becomes a necessary condition for mapping to be a projection. That's what we assumed. We assumed f is a projection, and we found that f square is f. Okay, we can also think of the converse. You can see whether this is sufficient condition to say that f is a projection map. The answer is indeed true. Let's check that. So let f square is equal to f, and we say that we want to prove that f is a projection. F is a projection onto image of f and along kernel of f. Okay, therefore it's enough to prove that v is direct sum of kernel of f plus image of f, and f restricted to image of f is identity map. That's what we saw some time back. Okay, so that's what we saw. That's a thing. Therefore, if you say this, then it's we have proved that f is a projection. Okay, let's prove the first part. So these two conditions to be proved, 1 and 2. So we assume f square is f, and then prove this. Okay, let's try to prove here. Suppose let's assume that let v belong to kernel of f intersection image of f. Okay, so we want to show v is singleton 0. I mean the intersection is singleton 0. Then we are done. So to show that, let's assume that v let's take an arbitrary element from the intersection. Okay, so for the intention is to show, the claim is to show that v is 0. Okay, that we'll try to see. Since v belongs to kernel of f, this means v belongs to kernel of f and image of f. Therefore this will imply that f of v is 0, and there exists a w in v such that f of w is v. Okay, because that's we are using the definition of kernel of f and image of f. Since it belongs to kernel of f, f of v is 0, and since it belongs to image of f, v has to be image of some element from the domain. Therefore let's say w is an element of v, image of that is 0. Okay. Now f of w is v. Okay, now you can easily see that 0 is f of v from this, but what is v? V is f of w, therefore f of w. Since v is f of w, so it's f of w, therefore this is nothing but what? This is f square of w, and since we know f square is f, that's the assumption we have, therefore this is f of w, and what is f of w is v, and therefore we have shown that v is equal to 0. Okay, that implies v equal to 0, and therefore v is a direct sum of kernel of f plus image of f. So that's clear. So we have to prove the next claim. This claim number 2. The claim 2 is we have to show that f restricted to the image of f is a identity map. Okay, let's prove that f restricted to image of f is identity map. That is very easy to prove. So what is given to us is f square is f. That is equivalent to say that for all v in v, f square of v is f of v. Okay. In other words, you can also write it as f of v is f of v. Okay. So let's say let f of v be equal to w. Okay. So let's, I am assuming just for notation purpose. Therefore, this means what? This implies this guy becomes f of w is w. Okay. And what is f of v? Since v is an arbitrary element of v, f of v is an element of w. Therefore, w belongs to image of f, and it's an arbitrary element of image of. Therefore, it means you have taken for every element of image of f. We have proved that f of w is w. Therefore, what does it mean? It means that f restricted to image of f is the identity map. and hence we have proved that F is a projection. F is a projection onto image of F along the direction of kernel of F. Okay, so that's what we wanted to prove here. So we are going to see a lemma. Okay, this lemma will be useful while proving the primary decomposition theorem. So the lemma is as follows: let V be a vector space over a field F, and let F1, F2, etc. up to Fk be k non-zero linear maps from V to V. So L of F1, F2, Fk belongs to L of V, V, and Fi is non-zero. So we are assuming k non-zero linear maps from V to V. Okay, if these k linear maps add up to identity, from 1 to k, Fi is I, the multiplicative identity of L of V, V. And the second condition, Fi composition Fj is equal to Fj composition Fi is equal to 0 for I not equal to j. Okay, so if you take two different linear maps from here, they commute and they also equal to 0. Then these two are sufficient to say that all these Fi's are idempotent operators. Fi square is equal to Fi. Fi square is Fi, and this also gives rise to a decomposition of V, namely V can be written as direct sum of I running from 1 to k image of F. So this is the lemma. Proof is not very complicated; it's very straightforward. So let's prove these two necessary conditions, assuming the sufficient condition. From first condition, we know that these Fi's are adding up to identity element. Fi running from 1 to k. So take an arbitrary Fi and then take composition both sides. Since composition is a function, this says that this implies Fi or Fj composition. Let's take J. Fj composition summation I running from 1 to k. Fi is Fj composition I. But Fj composition I is Fj because I is the multiplicative identity. So this is clear, and therefore we have to see this side. This side will give you Fj composition F1 etc. up to Fj composition Fj etc. up to Fj composition Fk is Fj. So that's clear. So we are just taking this composition inside and then we get this. From second condition, we know that when I is not equal to j, they are 0. Therefore, all these terms are 0 except this, and this is nothing but Fj square. Therefore, this implies Fj square is Fj for all j. So this is arbitrary Fj. We have taken j is arbitrary. Therefore, we have proved that these Fi's are idempotent operators or Fj's are idempotent operators. So the first condition is proved. Let's prove the condition number 2. Okay. So condition number 2, when you look at it, since Fi's are assumed to be non-zero linear maps, then we know that image of Fi is not the trivial subspace of V. So we know this. So it's equivalent to say that. Therefore, all these Fi's, images of Fi's, are non-trivial subspace of V. That's one thing. We try to prove this by two parts. First, we prove that V is sum of image of Fi's, I running from 1 to k, and then we prove that it's a direct sum. Okay, so the direct sum we'll prove the second part. So we'll first try to prove this. So first we prove that V is equal to image of F1 plus image of F2 etc. up to image of Fk. So we prove that this is subset of this and this is subset of this. This way is trivial because all this image of Fi is anyway subspace of V, and therefore this way is clear. I mean, if you take element here and add them, and they are going to belong to V. Therefore, this is a trivial. It follows from that. So we have to prove this way. So we take an arbitrary element from V and prove that they can be represented like this. So let V belongs to V and V belongs to V. Now, by condition 1, we know that summation I running from 1 to k Fi is I. Okay. Therefore we can say that therefore this can be written as, now V can be written as V is nothing but the identity of V, that is nothing but summation I running from 1 to k Fi of V, which is nothing but summation I running from 1 to k Fi of V. Okay, that's how addition is defined in L of A gamma V, and therefore this implies, this says that this says that V is a subset of image of F1 plus etc. up to image of Fk, and therefore we have proved this part. As I said, the reverse converse part is trivial, so we leave that as an exercise. It's easy to prove. Therefore, we are left with only proving the other part, that it's a direct sum. So how do we prove that for direct sum? So we assume that let suppose V1 belongs to image of F1, or Vi belongs to image of Fi, okay, for any I, okay, and V1 plus V2 plus etc. up to Vk is 0. So we are taking an element from all these subspaces of V, image of Fi's. We are taking, so let's say Vi be the element we are considering from image of Fi, and we also assume that they add up to 0. And the claim is, we will say that the claim is to prove that Vi all these Vi's are zeros. Okay, that hence proves that it's a direct sum. Okay, and suppose V1 V2 is Vk. Okay, and the claim is we will prove that Vi is equal to 0 for all I. Okay, now so what did we assume? We assume that Vi belongs to image of Fi. So this is equivalent to say that there exists W belongs to, or Wi belongs to V, such that Fi of Wi is Vi. So this is the definition of image of Fi. Since this element belongs to image of Fi, it has to be image of some element in V. Therefore there exists Wi in V such that Fi of Wi is Vi. That's okay. And so what we assumed is, we assume that V1 plus V2 etc. up to Vk is 0. Okay. Now let's take the image of this on both sides with respect to Fi. So Fi of V1 etc. up to Vk has to be Fi of 0, because Fi is a function. Therefore this implies this. Now this is nothing but what? Fi of V1 plus etc. up to Fi of Vi plus etc. up to Fi of Vk is equal to 0. Fi is a linear map, therefore Fi of 0 is 0. Is equal to 0. Now what is this? I mean, if you take this is Vi belongs to, so what is Vi? V1 belongs to image of F1. That means this V1 can be written as some F1 of some W1. Okay, that's the definition, right? Because V1, by assumption, V1 belongs to image of F1. That means equivalent to saying that, as we written here, it's equivalent to say that F1 of W1 is V1. Therefore, if V1 is this, therefore what is Fi of V1? Fi of V1 is nothing but Fi of F1 of W1. Okay, because that's what we get from here. That this implies 0, because if I is not equal to 1, Fi composition Fj or Fj composition Fi is 0. That's what we assumed as the second sufficient condition, and therefore this is 0. That implies what? This Fi composition V1 is 0, and the same argument will be true for all. So we can say that this implies Fi of Vj is 0 when I is not equal to j. The similar argument will work, because Vj belongs to image of Fj, and therefore image of Fj can be written as Fj of some Wj, and therefore you get Fi composition Fj of Wj, but Fi composition Fj is 0, therefore that has to be 0, therefore this is 0. So this is clear. Therefore you will be left with, in this side you will be left only with Fi of Vi is equal to 0. So this implies, by this analysis, this implies this guy becomes, because all the remaining terms are 0, so that vanishes. Now what is this? This is fi of wi is 0 because vi, that's what we take it here, but from definition of image of fi. This is nothing but fi square of wi is 0. But what is fi square is fi because it's idempotent operator, therefore this is equal to fi of wi equal to 0. Because since fi square is fi, that's what we first do. And therefore what is this fi of wi? Fi of wi is nothing but vi is equal to 0. And hence what we have proved is what we have proved is we have proved vi equal to 0, and this fi can be, this I is arbitrary here, therefore we can say that this vi equal to 0 for all I. And hence we have proved that, by assuming this we have proved that vi is equal to 0 for all I, and hence we have the decomposition as v is equal to image of f1 direct sum image of f2 etc. up to image of fk QED. Okay. Okay, so this is proved. So what you have just proved is, so we have proved that fi square is fi and v is the direct sum of image of fi's. Okay. Now it's clear that since fi square is fi, therefore these fi's are projection maps, projection onto image of fi and along the direction of kernel of fi. Therefore it's worth understanding what is the kernel of fi's. Okay. It is easy to prove that kernel of fi is nothing but direct sum of image of j running from 1 to k and j not equal to I. Okay. I mean, in other words, these fi's are projection maps onto image of fi and along the direction of kernel of fi, and the kernel of fi is this. So this can be easily proved. For the simplicity, let us assume for proof for 1. I mean, let us assume for we proof for kernel of f1. So what is kernel of f1? By this, what is kernel of f1? Kernel of f1 is direct sum of j running from 2 to k image of fj. Okay. So we have to prove this. So we prove by directly constructive proof. So we prove this and prove this. Okay. So let's prove the forward first. So we take an arbitrary element here and prove that belongs to here. So let v belongs to kernel of f1. That means f1 of v is 0. Okay. Now we have proved that v is direct sum of this guy. Therefore this v can be written as, v can be written as there exists w1 belongs to, there exists w1, w2 etc. up to wk belonging to v such that v is f1 of w1 plus etc. up to fk of wk. Okay, so that follows from the definition of this direct sum. V has to be written of, v has to be of this form. We are taking v belongs to kernel of f1. Though v belongs to kernel of f1, v belongs to v, and therefore it belongs to the whole of the domain, and therefore it can be written as this form. Now what is f1 of v? F1 of v is f1 of w plus f1 of f2 of w2, okay, w1 here, plus etc. up to f1 of fk of wk. And we have observed that f1, f2 and f1, fk are, since they are not equal, the indexes are not equal, they are all 0 maps, and therefore these are all zeros, and we are left with only one. This is nothing but f1 square of w1. Okay. And f1 square, since f1 square is f1, this is nothing but f1 of w1. And what is this one? What is the left hand side? Left hand side is 0 because v belongs to kernel of f1, therefore f1 of v is 0, and therefore the v is 0, therefore f1 of w1 is 0. So this implies v is nothing but f2 of w2 etc. up to fk of wk, and hence we have shown that v belongs to the right hand side because v is nothing but f2 of fk. Okay. Now conversely, we take an arbitrary element here and prove that element belongs to this one. Okay. Yeah. So, okay, sorry. Okay, so let's prove the converse now. So for the converse, what we will do is we will take an arbitrary element from the right hand side, and then we go. So let's say let let W belong to direct sum of j running from 2 to k image of fj. Okay. The claim is W belongs to, therefore the claim is W belongs to kernel of F1. That means you want to show that okay, F1 of W1 is 0. Okay. Now since it belongs to this implies by definition there exist V2, V3 etc. up to Vk belonging to V such that W can be written as F1, F2 of V2 plus etc. up to Fk of Vk. Fine. Now what is F1 of W? We want to show that F1 of W is 0. Therefore, what is F1 of W? F1 of W is F1 of F2 of V2 etc. up to F1 of Fk of Vk, and therefore we know these are all zeros, and therefore F1 of W is 0, and therefore W belongs to the kernel of F1, and hence we have shown that kernel of F1 is nothing but direct sum of j running from 2 to k image of Fj. Therefore, these projection maps are projected along the direction of this and onto the image of Fi's. That's what we wanted to claim. Okay.